Hi, I'm David. In this fourth basic electrical module, we're going to be looking at circuit faults. Knowing how to locate these faults will help when it comes to diagnosing them. We'll go through the step-by-step procedures both on the test board and on the vehicle. There are many different types of faults that can occur in electrical circuits. We'll be looking at open circuits, excess resistance, short circuits, short to ground, and shorts to voltage. An open circuit is a break in a circuit that stops current flow. This can occur anywhere in the circuit, in the wiring, in the component, in a fuse, or in a ground. Voltage drops can be used to find an open circuit. You're looking for battery voltage. The reason for this is that the multimeter is completing the circuit. One side of the open circuit will be connected to the positive side of the supply and the other side to the negative. Here we have a 3-globe parallel circuit with one of the globes not working. The fault could be in the globe itself, in the positive side, or the negative side. I'll use a voltmeter to check my readings. Across the globe, 0 volts. Across the positive side, again 0 volts. Across the negative side, we've got battery voltage. That indicates that the open circuit is on the negative side. Remember, when you're looking for an open circuit, you're looking for where the voltage is, not where it isn't. A resistance in a circuit will cause a voltage drop across that resistance. This means that there will be lower voltage available at the load or the sensor. In the circuit shown here, we measured the voltage drop across the solenoid while it was operating, and it was only 8 volts. This means that there is approximately 4 volts missing. This must be caused by an excess resistance in the circuit. Measuring the solenoid, we get 8 volts. It's now an elimination process. First, which side of the load is the excess resistance on? Measuring from the battery to the positive side of the solenoid will give the voltage drop on the positive side of the circuit. If there is an acceptable voltage drop, usually no more than 3%, then it will be necessary to check from the negative side of the load to ground. Now that we know which side the fault is on, we can narrow our search. If on the positive side, we keep one probe on the solenoid and start to move the other closer step by step until the missing voltage disappears. The position of the resistance will be the previous connection or the component. In this case, it would be the switch. The same test could be done on the negative side of the solenoid if this is where the fault was located. Returning to the board, I have a resistor in series with one of the globes. Turning it on, it doesn't appear that there's much difference in the brightness of the globes. I'll measure the voltage drop. The voltage drop across that globe there is roughly 12 volts. And across this globe here, we have 11.35 volts. Even though it appears to be the same brightness, it doesn't receive the same voltage. If we measure the voltage drop across the resistor, 0.63 of a volt, there's our missing voltage. So a resistance in a circuit will cause a voltage drop. If I move the resistance to replace the wire at K and L, and then turn the circuit on, you'll see that all of the globes are a little bit duller this time. We'll check the voltage drops. The voltage drop across the globe is now around about 10.1 volts. It's lower than it was before. The voltage drop across the resistor is 1.85 volts. The voltage drop is now higher on the resistor. Why is this the case? This time we have the current of all three globes flowing through the resistor, whereas in the first test we just had the current of one globe. So the more current that flows through a resistor, the higher the voltage drop, even if the resistance is still the same value. The definition of a short circuit is where the current takes a shorter path than originally intended. Some of the resistance is bypassed, so more current will flow. This current may exceed the rating of the fuse, causing it to fail. A short to ground is where the current takes a shorter path than originally intended to ground. This will cause more current to flow. The current may exceed the rating of the fuse, again causing it to fail. A short to voltage is where the current takes a shorter path than originally intended to voltage. Again, this will cause more current to flow, and if this exceeds the fuse rating, will cause it to fail. This is the schematic of the circuit we'll be using on the test board. It's a 3-globe series circuit. I'll start by measuring the voltage drop across each globe. .5 volts, 3.8 volts, and 3.8 volts. I'll put a bypass in. I'll bypass this globe here. And as you can see, the current has now increased. I'll measure the voltage drops across the working globes. .6 volts, and again 6 volts. The voltage drop across this globe will now be 0. Because this bypass is going to ground, this would be a short to ground. This is how the schematic would look with the short to ground. If I remove the short to ground, and bypass this globe, you'll see that the current increases again. Because the bypass is now going to the positive side of the circuit, this would be a short to voltage. The voltage drop across the globes will increase, and the current will also increase. On the schematic, this is what the short to voltage would look like. We're back to the 3-globe parallel circuit. If the short circuit causes too much current to flow, the protective device will operate. There's several methods of finding out the location of the short circuit. All methods require removing the fuse. In the first method, we'll use an ohm meter. Connect the meter from ground to the circuit side of the fuse. Now remove all of the loads. Turn the circuit on and check the resistance. If the meter reads open circuit, then the short circuit must be in one of the loads. If there is a low resistance, the fault must be in the wiring. In the second method, I'll use a voltmeter. I've got the fuse removed and the voltmeter is connected across the fuse holder. I'll now remove the loads. In this case, it's the light globes. I'll turn the circuit on. If there's a voltage reading, that indicates that the short is in the wiring. If there's no voltage reading, that indicates that the short is in one of the loads. My preferred method is using a test light. It must be at least 21 watts. I've got the fuse removed from the circuit, and I'll connect the test light across the fuse holder. And I'll turn the circuit on. You can see the light is glowing bright. That indicates that we've got a short in the circuit. Next thing I do is remove one load at a time. The light's still bright. I'll remove the next load, no change, and the last load, still no change. That indicates that the short is in the wiring. So now what I need to do is go to each connector and disconnect, looking for the light going out. No change. Again, no change. The light's gone out. So obviously, the fault now has to be in this part of the circuit. I said to use a 21 watt light globe, minimum. Why? Surely a normal test lamp will do the same task. We'll have a look at the difference and see. I'll connect my circuit all back up again. There's our light globe with the short in place. If I remove the short circuit, you can see the light goes dull. That indicates that there is no short circuit. I'll now replace this test light with a standard type test light. No short circuit. Short circuit. You can see there's virtually no change. So you can't tell whether you've got a short circuit or not with a low wattage test light. The higher the wattage of the test light, the better the result will be. This is because as the wattage of a light goes up, its resistance goes down, so it has less effect on the circuit. Let's have a look at a couple of these faults on a vehicle. The customers complain that after driving the vehicle at night, it's a little bit hard to start in the morning. Of course, there could be a number of faults that cause this. Battery, alternator, even the wiring. I'm going to do a voltage drop test on the wiring to see if it's okay. To check the wiring from the alternator to the battery, I'll put the red lead on the B+ terminal of the alternator and the black lead on the positive battery terminal. Now I'll start the engine and take a look at my reading. If my reading is greater than 3% of battery voltage, I have a problem. If not, I'll turn on the headlights and the rear demister and check again. If the voltage has not increased significantly, then the cable is okay. If the voltage did increase to nearer the 3%, then you would have to check for excessive resistance in the cable. If the positive side of the circuit is okay, don't forget to check the ground side of the circuit, as this will connect the alternator to the negative terminal of the battery. There could be an excess resistance in this part of the circuit also. The customers also complained that the right-hand front parking light and right-hand rear tail light are not working. I had a look at the schematic and found that they come from the same fuse. I'll now check to see if it's failed. The fuse is blown. That indicates an excess of current. What I need to do now is fit a test light. This one's made from a blown fuse and a 21 watt globe. I'll replace the fuse with my test lamp and turn on the parking lights. As you can see, the globe's glowing brightly. That indicates a short in the circuit. What I have to do next is remove each of the loads, one at a time. In this case, it will be the light globes. And then I check the test light between each one. Starting with the right-hand front park light, I'll remove the globe and then recheck the test light. The light is still bright, so I'll move on to the right-hand rear tail light and license plate lights. With all the loads removed, the light's still bright, indicating the fault is still there, so it must be in the wiring. Unplugging the connectors in this circuit will isolate the fault. I'll start with a license plate harness connector in the tailgate. With the trim removed, I can access the connector that needs to be unplugged. This time the light didn't come on, so the fault must be in the right-hand license plate light harness. If the light didn't go out, you would then move to the next connector along the circuit. When the test light goes out, you will have isolated the fault to a particular part of the wiring harness. That's the procedure for locating open circuits, excess resistance, short circuits, short to voltage and short to ground. Using these simple methods will make it a lot easier to locate and repair these faults. And always remember, training is the key to your success. Bye for now.